So yeah, I'm Gary Greider. I'm the High Performance Computing Division Leader at Los Alamos. I've been inside the weapons complex since 1981, so I guess I'm an old person from that point of view. And when Megan asked me to give this talk, I wondered about it because I'm nowhere near an entrepreneur. I've worked for the same company for a long time, so I'm not sure that's very entrepreneurial, but we do a lot of technology funding, and we come up with a lot of ideas that could be funded. And so I think that's a theme here for me. Is we do a lot of stuff. We have a lot of problems that are hard to solve, and we oftentimes fund people to solve them, and we oftentimes even give them the solution and let them build it. And so hopefully there'll be something here for everybody. Just a reminder of what Los Alamos is. It's a national nuclear weapons lab that maintains a nuclear stockpile for the U.S. government. We've been around since the 40s, so we're pretty old. We've been computing for a long time as well. About 8 decades worth. We built a machine shortly after being the first user on ENIAC, the first machines in the US. We built our own version of it called Maniac, and ever since then we've been building machines at Los Alamos. Involved in the stretch machine, which became the IBM 360 architecture, which was pretty famous for years. We got the first Cray one, serial number 1. It came in and didn't work, just like most machines that we get. They come in and don't work. CM2s and CM5s, those were interesting machines, and so forth, all the way out to putting in Trinity now. Trinity is a pretty large machine. I think I talk a little bit about it here in a minute. We even have a D-Wave machine. It's a quantum annealing machine, and we're starting to use it, trying to figure out how it might work into our problem-solving environment. And then there's actually an RFP on the street right now as we speak. I think it's due back Friday for Crossroads. It's a machine in the 2020 time frame that presumably would be about a third or 3x or so bigger than Trinity. So anyway, we've been at this a long time. The machines we get typically don't work, and we have to make them work. I thought I would pull this out of our archives. I've been involved in an archiving project at the lab for the last few years to try to archive and pull and put together the history of computing at Los Alamos. And this is the original letter from Los Alamos procurement to Seymour Cray. And I noticed that Seymour Cray was on your website as an example of a startup, and so I thought this was kind of cute that it matched your website. This is the letter that started it all for him. It's digitized and preserved forever. Now I thought I'd take you through some examples of the past of how HPC has really led things that have gone into industry, how trickle-down really works, and tell you some of the things that if you just have thought about that when we were doing this, if you'd have thought, gosh, that's going to become the video industry, you might have gotten pretty rich on it, right? So we had this machine a long time ago. It was Thinking Machines. It was in the early 90s. It turns out it was the first top 500 list on the first top 500 list. It was the top machine on the first list ever. And it was a big SIMD machine, and all the tools required to do SIMD were done in this era. And it turns out that all those same tools, SIMD, basically how CUDA works, all those sorts of things, that's what became what's in a GPU today. So it used to be a machine the size of, I don't know, it was pretty big, right, the size of this room. And now it's in that card. But it's the same technology. All the ideas to produce that Tesla, that's what that machine was. And so I think that's important, right? Because if you look at HPC and you look at what we're doing now, well, someday something's going to pop out the other end that's going to be pretty important for the rest of the world. And this is a really good example. So what about storage? Because I'm the old storage guy. So there's a lot of examples, right? So data tree was written in the 70s for holding our archive, and it was commercialized, right? And there was 20 sites that took it on and used it for years and years, and it was done by General Atomics. There's Unitree. Unitree came out of Livermore. It was a similar thing. It was written based on early versions of Unix. Data tree was based on IBM MVS technology, and it was popularized and went to 20 or 30 sites. So these are all really old 70s and 80s and 90s examples. HPSS is another one, right? So we we put that out. We basically had this need for a parallel archive. We more or less said, here's the solution, here's how you do it, and IBM decided that they would do this. So IBM Federal is the one that built HPSS for the most part with the lab's help. And there's been lots of offshoot products out of that actually started startups. Some more examples. So SAMQFS, that's essentially, to some extent, an ex-Livermore thing, and it's become lots of things, right? But Versity is its current, variant. Slurm is another example, right? Slurm came right out of Livermore Workload Manager, and now it's a company. Gluster FS was an RFP to buy a cluster in the late 90s or early 2000s, I think it was. And they needed a file system that scaled, and that's where Gluster came from. And so all these things are really good examples of technology that escapes the lab and becomes startups. Things that I was more involved in, Panasys, GPFS, and Lustre. So, Panasys came right out of an requirements document that the Tri-Labs wrote. We worked with Panasys, what was to become Panasys, for a year trying to convince them to take our money to build their thing. They decided to go after venture capital. They went out and got venture capital, but they used our solution space and our requirements document to build their file system. GPFS wasn't GPFS at the time. It was called Parallel I/O Library or something like that. And I think we successfully convinced them to move on and build what's now GPFS. And we didn't end up funding much of that, although we bought enough hardware from IBM that they had plenty of money to go do this. Then Lustre is pretty famous around the HPC parts, right? And 4 years of my life working with Peter Brahm to get it built. But that came directly out of this whole effort. So essentially we funded the beginning of Lustre all the way through its middle age. And then we let it go to see if it would float. And it's still floating. It's got some battle scars, but it's still floating and moving forward. So that's another good example of something that transferred out of the labs and into industry and became quite a big thing, right? I mean, it's a big industry, the Lustre part of HPC. There's lots of sites. I don't know how many, but certainly thousands. Another interesting example. Yeah.
So there's one missing little subset for your slide, which is HyperCloud. So we used your government resources, especially the Hyperion supercomputer, together with Intel for half a year about to go from single node, single container to multi-node, multi-container.
Right.
I can imagine it's a real challenge.
Yep.
And we did that. So,
cool.
Yeah,
providing machinery is another good story, and not just Hyperion, but there's other good examples of that. Another really good example of that is when we retire machines, we actually are partnered with the National Science Foundation. We give them to this center called Probe, and that's a place where people can go and use thousands of machines. They're old, but there's thousands of them. And you can be mean to them, and you can be rude on them, and you can do whatever you want to. You heat them up, there's plenty more. There's just stacks and stacks of them, right? And so you can use them and so forth. So, I mean, that's a really good use, and industry can use that. So it's a good point. Ceph was an interesting model, right? So Ceph came out of an academic alliance. We funded the University of California, Santa Cruz for 9 years. We went to them and said, gosh, it wouldn't it be nice to have a parallel file system that had a scalable metadata engine? And, I'm still saying that today, oddly enough. But that was the problem we took to them. This was like 12 years ago, maybe 15 years ago or something like that. And we said, gosh, it'd be nice to have something where I could put 1 million files in the same directory and it wouldn't fall over. And gosh, it would be nice if I could walk directory trees and the security model of having to walk all the way up the tree and back down for every time you touch a file, that's going to be annoying in a big parallel system. It'd be nice to fix some of that. Why don't you go study that? They came back with a proposal that said, well, we'd like to spend the first 5 years developing a parallel file system in user space that's object-oriented to use as a research vehicle to go research your problem. And we said, fine, okay, $300,000 a year for 5 years. Here, go build this thing that ended up being what's now called Ceph. And of course, we funded Sage's education in the process. And well, lo and behold, it's become something today that we don't necessarily use it much in the labs, but it's become a pretty big thing in industry. It turns out that they really didn't fundamentally solve either problem that we gave them, but we learned something about it. But it's an interesting example of something really pretty big in industry that came out of a funding effort at a university. HDF is another one. We've been funding the HDF group for years, and that's a sort of a private concern that is a startup in a way. PNFS, there's been products that have come out of that. We basically started that effort at the University of Michigan a long time ago. And then another one that's really interesting technology is Tokutech. That's the cache oblivious trees, or what has become a really big industry, which is the log structured merge tree stuff that Facebook published and it's called LevelDB. You may not know what LevelDB is. And React, and there's a whole bunch of other stuff that has come from that. And it all started from this cache oblivious tree work that we did at Rutgers and Stony Brook and MIT years ago. They actually put this database underneath a BDB, a Berkeley DB interface, and made enough money to get to the point where we could get them a DOE small business grant. And now some company gobbled it up and bought it, and I don't even know what all it's in now. But that's a really good example of where a university person, came to us and said, we've got this really cool idea. We can do batch updates into databases instead of single record updates, and still do queries pretty quickly using log structured merge trees and the like. And so, anyway, that's a really good example, and those guys are really good guys. Just recently, we waved our arms and said, gosh, we need this thing called a burst buffer. And 2 or 3 years ago at supercomputing, I think burst was the most overused word. And so there's products that are out there now that are based on this. Cray built this thing called Data Warp, which is essentially a burst buffer, a tier of storage in between memory and a file system. DDN has this thing called IME, the Infinite Memory Engine. So lots more examples. So enough on the examples. Just I wanted to take you through the fact that a lot of stuff like that has become industry standard products that started with startups, that started with problems and ideas around the national labs problem set. So just to take you through some of the economics of where we've been and where we're going, to try to give you an idea maybe where the problem sets of the future lie. The economy really shapes what we do. We buy what we can afford to buy and try to make it work. And what you see in the upper left-hand corner was back in 2009 or so, I did this spreadsheet study that said, are we going to be able to buy disks forever and do parallel file systems forever and dump our memory out to parallel file systems forever? And it turned out that because disks get faster much more slowly than they get denser, there was a problem. We were buying disks at the time for capacity and getting the bandwidth for free. At some point, it turned out that we were going to be buying disks for bandwidth and getting the capacity for free. Buying disks for bandwidth and getting the capacity for free. And disks aren't priced for bandwidth, they're priced for capacity. And so that turned out to be a pretty bad deal. And so we sort of invented this idea of doing hybrid and putting a flash tier in front of the disk. And that was back in 2009, and that's where burst buffers came from. My running joke on this graph is it's the first time I ever got to put millions of dollars on a log scale. So I was pretty proud of that moment. But anyway, so economic analysis sort of tells us where our big problems lie. We did the same thing with economically modeling where the tier below parallel file systems below disk. In the past, for us that's been parallel tape. HPSS was the solution space for that, but essentially it's parallel tape. We did the study on that to try to figure out if we could afford to continue that way of doing business. And you can see that over the I've been doing these models for 25 years or more, and the models are based on sort of 3 memories a month essentially the amount of data you grow in your archive at an HPC site. And I did the model based on when we're going to buy big machines and how much memory they're going to have, and you can see that there's two big spikes, and that's when new machines show up. 2015 is Trinity, and 2020 is Crossroads. And always in the past, the cost of the archive is equal to the cost of the media. That turned out to be not true anymore. The new tape drives is the red part of those towers, and you can see that tape drive costs started to become pretty significant, tens of millions of dollars. And so it didn't seem like that was going to work out too well, so we invented this tier of storage that we call campaign storage that goes in between parallel file systems and tape archive. And so anyway, economics drove most of this activity, and lots of activity within industry to try to solve those problems. And this is kind of a pictorial view of how that went, right? Before we had Trinity, this was our model: memory, parallel file systems, and archive. After we've added these two tiers, burst buffer and campaign storage, and you can get an idea of the sort of scale that we're talking about over on the right. 1 to 2 petabytes a second of the memory bandwidth in these machines, and a couple of petabytes of DRAM. So it's a lot of DRAM. 4 to 5, 6 petabytes of flash that runs at 4 to 5 or 6 terabytes a second. It's overwritten every hour or so, so about 10 overwrites a day. And then the parallel file system runs at about a fourth that speed, a terabyte a second. It's maybe 100 petabytes or something. And then the campaign store is even bigger, but even slower. And then the archive is just dirt slow, and that's just to store stuff that you really want to keep forever. So anyway, we had to add these tiers, and why would I bring that up? Well, because there's the opportunity for innovation in these new tiers, right? That's the opportunity for software writers and people building hardware and things to build things that are interesting to solve those new tiers of storage and to solve the management of this more complex tier, a tiering system than we have today. And so, anyway, that's what that looked like. But you've got to start asking yourself, do you really need that number of tiers? Or is that just a sort of a temporary, economic anomaly? Or is that the way you're going to head down the path for a long time? It looks like this is sort of temporary, and it looks like basically that the burst buffer tier is sort of finding its way down into the parallel file system tier because of the cost of flash continues to go down. And the number of fabs that are producing it continues to go up. And it's also finding its way up into some of the slower parts of the memory applications. And so that tier is growing. This capacity tier, this campaign tier that we said we needed, is finding its way down into the archive, and it's also finding its way up into the parallel file system tier. So it looks like at some point, maybe some of the tiers may disappear. Could be parallel file systems kind of disappears into partly above and partly below. It could be archive tier goes away altogether. We'll see, but that's opportunity too, right? So if you look at it, there's opportunity to make this happen sooner. The people that have software out there that are ready for this will end up winning. The people that have hardware out there that are ready for this will end up winning. And we're pretty sure that we're going to get bids for Crossroads that have no spinning disk, which kind of proves out this theory that that the IOPS tier is going to eat its way down into the parallel file system. Another way to look at this and more information that's out public on the web is this thing called our workflow. So we've been buying machines forever. We've always bought them based on the fact that we wanted applications to run n times faster than they ran before or n times bigger than they ran before. But what's turning out to be true is that the flops are free and the infrastructure costs. And more the infrastructure is costing more and more as a percentage of the total cost of ownership for these big machines and environments. And so we've decided that instead of telling people we want applications to run 6 times bigger, we say we want to get 6 times more throughput through this machine in its 5-year life. And part of that is running the application bigger and faster, but a lot of that is how much data do you have to move around, and when does it need to be there, and so forth. So we did a pretty exhaustive study of our applications. We looked at a typical simulation pipeline. It's got checkpointing, it's got visualization, it's got analysis, and you can see that we used a temporary, campaign and forever as our durations, or the durability, or the retention of the data, and so forth. So this information became pretty interesting and pretty useful for people bidding on next generation machines, because so much of the cost is not flops anymore. So much of it is pipes and storage devices. So I think there's opportunity there. If somebody wants to pick that information up and read through it and find and figure out, what, I can do something about that. I should invent a product or go talk to Intel or whatever. That's opportunity. So the emerging themes, we've got this performance and IOPS tier. That looks like it's going to be solid state of some kind. Might be in the neighborhood of 10 terabytes a second by 2020. And it's basically to keep data around for hours to maybe a week or something. We'll probably have a capacity tier. It'll probably be mostly spinning disk, because the sheer volume of fabs to create flash is not going to be high enough to service that need in that time frame. So it's very likely going to be spinning disk. Probably more like a terabyte a second or something like that, and many, many exabytes. We're also moving to a different kind of model for how we get data into the machines and out of the machines. Instead of using the data, in the classical file system sense, open file, read, and so forth. More likely you're going to do something like a checkout, check-in mechanism, where you check out large volumes of data and metadata, and have it and use it on the machine inside the flash for a week or two, and then check it back in using versioning and producer consumer models and things like that. So we're seeing a move away from an interactive interface to that capacity tier and more of a batch interface, which is what this means. We're also hoping that we can up our game on metadata. We all are lamenting the fact that we've gone through 3 generations of archives, and we've stored petabytes and petabytes and hundreds of petabytes and exabytes of data, and there's precious little metadata associated with that data. And 70 years later, no one knows what the hell it is, right? I mean, we can kind of figure out that it's 7-bit ASCII instead of 8-bit, and we can kind of figure out that some of it's 56-bit words instead of 64-bit words, just by looking at the data structures and things like that. But really knowing what it is and getting use out of it is just not there in the HPC community. And the problem is the ability to store and query metadata has not been there, still isn't there. And the ability to capture it, to capture the provenance that as the data is produced, is not there. However, we're in the midst of changing out our programming models. We're moving from pure MPI type programming models to brand new programming models, where you're going to have to provide the machine far more information about what your data looks like, so that the programming models and the runtime can optimize around it. Because you're going to have to provide more information to the runtime, we can capture that information and use it as metadata and keep that with the data forever and from now on, so that we can answer interesting questions about all that data we've stored years later. An example might be, we realized just now that 10 years ago, we ran a simulation set that was just wrong. And we only realized it 10 years later by some resolution thing we were able to do 10 years later that we couldn't do then. So the question you got to ask yourself is, how many decisions did we make based on that wrong calculation we did, because we didn't know any better at the time? And what does that mean for the nuclear stockpile? And what does that mean for the nation? And are we putting the submariners in jeopardy? And we shouldn't, right? And so we can't answer those questions today unless it's answered by a person. It can't be answered through data. There's no way to get that information from that data. And what we'd like to be able to do is capture enough information to be able to do that. Unfortunately, that means not just 1 order of magnitude more metadata. It probably means 10 orders of magnitude more metadata, because you don't know what question you're going to be asked, and so you've got to keep a lot, right? And so we're expecting a huge increase in the amount of metadata we have to keep per byte of data that we store. Just huge. And we hope that that happens, because otherwise keeping all this damned old data is not worth time. It's not worth the effort. So at any rate, we're hoping that the metadata problem can be alleviated, and I think there's huge opportunity in there. And then energy efficiency. We all care about energy at our sites. Storage systems don't eat up most of the storage or power at our sites. Certainly, computing does, but more and more. I mean, if you have 100,000 disk drives, it's still quite a bit of power, and so there's some opportunity in energy efficiency as well. So I basically tried to build some potential candidate technologies or ideas that people could take off and run with if they wanted to. The first one is this idea of check-in, check-out. It's really not been done before in HPC. It's not been done in parallelism, but it's certainly been done before. AFS and other kinds of things like that over the past did this sort of thing. There's some good research going on at Carnegie Mellon, the IndexFS and BatchFS systems. It was the best paper at supercomputing last year. I think that's interesting stuff there that could be productized. This two tiers idea of check out and check in is a good example. Mercury is an open source forwarding layer that needs to be productized because the labs suck at productizing things. It's better off in industry hands. PF tool is a very interesting parallel data movement tool that is incredibly powerful, incredibly parallel, automatic load balancing, all kinds of wonderful things, but it needs some productization. Some other areas of potential, so they might have producer-consumer type things or remote access. DI mmap, this is done at Livermore. It's a version of mmap that actually works pretty well for true out-of-core, because mmap typically doesn't work very well for out-of-core, but they did some really cool work here that makes it work pretty well. So that's really interesting work that I think has a place in graph analysis and other kinds of places. Remote memory file mapping also, there's some work that's being done there that probably would be interesting for a larger industry setting. And then performance and capacity tier oriented tech transfer potentials. There's this thing we've written called MARFS, which is a namespace that sits on top of objects that scales really, really, really well. We just did a study to see how well it scaled. We ran it on a retired machine, 8,000 node retired machine, and we got 815 million inserts a second. And we built a single directory that had 915 billion files in it. And we could still stat one of those files in less than a millisecond. So it's pretty interesting technology. This two-tiered erasure thing that we're building an erasure system that sits on top of an erasure system to get better reliability than the classical erasure systems that are out there today in industry, which I think is kind of interesting. It's open source. It's based on this Intel storage acceleration library, which is kind of neat. It uses the vector processor in the Intel machines to do erasure. Anyway, parallel log structured file system was a thing, a few years back at supercomputing, and OpenZFS is another variant of things that probably there's innovation that could be done there in the open source and startup community. So I think I'll close on that. I think that's basically my last slide. There's resources out there, the labs. There's ECP, the Exascale Computing Project. There's NSF research calls. Talk to an HPC storage expert. Send me email if you have a question or if you have an idea, or if you're looking for a problem to solve, because we have plenty. Anyway, that's my last slide. It's got some GitHub resources on there, and that's actually not a picture of me, but I was there shortly after that. So, thank you.
Thanks so much, Eric.